Yeah, Raj, just go ahead and take a, yeah, okay. So again, guys, just take screen captures of that and please email it to me. They finally approved that Twidla site, and so they said they were going to work on making it so they know what's causing the audio to be blocked. So that way I can send this to them and they know it's still a problem. Yes, and Mike, they know about this, and they said it's approved now, so it shouldn't be blocked, but they know what the problem is. So hopefully they can get it worked out. I'll just send them a bunch of these so they know it's still a problem. Okay, well, I'm going to go ahead and get started. And I've never tried this before, so we'll see how this works. We're going to try to do a finish up the PowerPoint notes. Thanks, Raj. Okay, can you guys see the PowerPoint notes I have up here? I'm assuming you can, so that's going to be a problem. If not, can somebody chat? Yeah, okay, good. All right, so I think we already started talking about this yesterday. Of course, we looked at the hard way to do this. We could sum up all these charges and do some calculus here, but we saw that there's an easier way using the idea of this electric flux. And so we can use a Gaussian pillbox that mirrors the surface here. And you guys said yesterday that was a cylinder. And so we've got it on there. We've got this cylinder, this Gaussian surface that we've drawn. And the last thing I think I left you with was I asked you to think about the E field that's pointing through the Gaussian pillbox. And I think you guys said, or you realized, that that E field is pointing everywhere outward on the surface. And keep in mind, this is a three-dimensional cylinder, and everywhere on the surface it's pointing directly outward. Therefore, the A vector is pointing outward too. So when I sum up the E dot dA, that's going to give me the E field times the area of the cylinder. And the area of the cylinder is given by 2 pi r times the length. I think that's the last thing I remember. I think Emily told me that. And so that's where we're left at. So the truth is we didn't do any calculus over here on the left-hand side, even though we have the calculus symbol. And the reason why we don't have to do that, the E field is constant. It's the same everywhere. The only thing that's changing is the area. Well, you guys should know what the area of the cylinder is. Therefore, you're not really doing any calculus. Okay, we also know that the flux is also equal to the enclosed charge over epsilon naught. In this case, the enclosed charge is related to lambda, because there's a certain charge per unit length, lambda. So if I take the lambda times the length, that'll give me the enclosed charge. So lambda times the length gives me the enclosed charge. So now I can set these two equal to one another. Now I can solve it for the E field. And so E field equals 1 over 2 pi epsilon naught times lambda over r. Any questions? Okay, so I want you guys, I'm hoping this works, I want you guys to kind of vote then. Here we've got this relationship here. I want you to say whether, if you were to graph E field versus R from this wire, what kind of relationship it would be. Uh-oh, what happened to it? It went away. What the heck? Dang it. There it is again, sorry. So if you guys go to this, there we go. If we go to this site here, you can vote. You can say whether you think it's a linear relationship, a direct relationship, inverse square relationship, or no relationship. Let's see, we have got 11 people in the class. Well, actually, we've got 10 people in the class. So I want to see 10 votes, please. Got 2. Keep on voting. But I'm not seeing voting that I'm thinking that people aren't really here for. All right, 6 more. Three people not voting. We're waiting. It says the site doesn't exist. What are you talking about, Raj? You're typing my name wrong. Polev.com and then Mark Lundfest, but it doesn't have the E on or the Y on the end. Come on. Okay, well, that's right, Alex. You get on them. Okay, so I'm going to assume you guys are going to get that figured out here pretty soon. Pretty soon. What I want you to remember is, first of all, we did an activity where we're comparing the different fields, and we kind of thought that this might be an inverse relationship. Okay. Then Michael said, you know, I don't like this kind of thinking thing. I want some real proof. And I said, okay, we're going to do a lab. We did a lab, and we also saw an inverse relationship. And then we did the brute force way of integrating Coulomb's law that you guys absolutely hated the other day. And we also saw an inverse relationship. I want you to think about how easy it was to find the inverse relationship, though, using Gauss's law. Okay, much easier, right? Okay, so we're going to go ahead and go on to the next slide, maybe. There we go. Okay, so we have another example here. Charge is distributed uniformly with a surface charge density sigma. Okay, so before we had a line charge, and we had a certain line amount of charge per unit length. Now the charge is going to be smeared everywhere on a plane, and there's going to be a certain amount of charge per unit area. And so I'm going to call it sigma, because it wouldn't make sense to keep track of and where their locations are. Okay, so it's smeared over this very large surface, but it's a non-conducting flat plane. Determine the electric field at points near the plane. Okay, so we've actually already thought about this, so we kind of know what the answer is. We've also done a lab, so we kind of know what the answer is. And now we're going to use Gauss's law to actually verify what we found. Okay, so what I have to do is I have to pick some kind of Gaussian surface that will mirror the geometry I have here. So remember, here's the thing with a Gaussian surface. It has to enclose a volume. So can somebody text or say something? What kind of shape would be a good one for Gaussian pillbox here? Rectangular prism, yeah, some kind of rectangular prism. Here, what I've chosen, a cube. A cube would work fine, okay? Because those things you can find the area perfect. Those all would work because you can find the area of them. I'm going to choose a cylinder because I can find the area of the end piece here. It doesn't matter. Your rectangular cube is fine. My cylinder is fine because I know how to find the area of a circle. You guys know how to find the area of a square. Either one would work. Okay, so Gauss's law says I would sum up all the E field and E dot dA elements. Well, be careful that you make your cube go on both sides, or your cylinder on both sides, or your rectangular prism go on both sides of the plane. Notice how mine's sticking out over on the other side too. So there's going to be E field on the right of the plane, and there's going to be an E field on the left of the plane. But notice how it's only going through the top surface of your rectangular prism, or your cube, or in my case here, my cylinder. It's not going through the edges of the cube or my cylinder here. It's only going through the top surface and this bottom surface. Okay, so I could add all these together, but tell me something about the E field here. Does it ever change? Somebody type in, does the E field change through the surface? No, that's right. How about on the back surface? Does it change? No. How does the magnitude of the E field on the front surface compare to the magnitude on the back surface? How does the length of the vector on both sides compare? Somebody type in, how does the length of the E field vector on the front side compared to the E field vector on the back side? Same. Okay, same. Good. Nice. They're the same. And so that means for this integral, the E can actually be factored out. It's constant. So it's not a variable. The only thing that's a variable is the area. But we're not going to do any calculus here because, I mean, it's kind of like trying to kill a bug with a bazooka. I don't need to do any calculus. I mean, I can find the area of this circle, or you could find the area of your square. You don't need to do calculus. So that's going to be equal to E times A, but since there's this front surface and there's the back surface, it's going to be 2E times A. Now, the reason I'm using A here instead of putting in pi r squared is because maybe you guys chose to use a cube or maybe a rectangular prism or something like that. And so I'm just going to say A for area. Any questions? Okay, well, we know that's equal to the charge enclosed over epsilon naught. Well, that's where it's a little bit tricky. I don't have a Q. I have a sigma, charge per unit area. So if I know the charge per unit area, how could I figure out the charge enclosed? What would I have to multiply the sigma by to figure out the charge? Somebody type in so I know you're thinking. Yeah, I'm going to have to multiply by area. So Q enclosed over epsilon naught. The Q enclosed is going to be sigma times the area over epsilon naught. Now I just set these two equal. I have 2EA equals sigma A over epsilon naught. The A's cancel, and I get E is equal to sigma, which is a constant, over 2 epsilon naught. Okay. Again, the sigma is just a variable. It's the charge per unit area. So many, let's say it's like 3 coulombs per square meter or something like that. And this is also constant, epsilon naught, permittivity of free space. That's a constant. So again, I want you to vote. See if you guys can get to the right place. I'm expecting maybe 12 or so. Let's see. If you were plotting this versus R, what kind of relationship would this be? I'm expecting I should have 11 people voting. Still waiting for a couple people. Okay, well, I'm assuming they must be having some problems. So it looks like to me you guys are saying there's no relationship. In other words, you're saying it's constant. Okay. So if you think back, we've already done some activities here. Remember, we're comparing the E field here on Earth, or excuse me, the gravitational field here on Earth to the electric field for an infinite plane. And we said it would be constant. Okay, and then we did a lab to prove that it was a constant. And now we've used calculus. I'm going to put calculus in quotes because not really calculus. Gauss's law, smarter than calculus. Don't tell Ms. McCombs I said that. We used Gauss's law. By the way, Gauss was an excellent mathematician. We're using Gauss's law to see that it is a constant. There's no relationship here. Okay, well, let's move on then. Okay, so now we have a different configuration here. Determine the electric field just outside the surface of any good conductor of arbitrary shape. So now I have this conductor. So imagine, I don't know, a sheet of thick metal, and it's kind of maybe the hood of your car or something. And it's molded and it has different shape to it. Okay. Those charges, remember, they're free to flow and they can move anywhere. And tell me, if you have, let's say the hood of your car is positively charged. tell me something about those charges. Do they like being near one another? How will they distribute themselves? Somebody type it in. They repel. Okay. So they're going to kind of be kind of smeared out over the surface, right? Does that make sense? If you have any net charge, yeah, they're going to move away from one another, but eventually they're going to get as far away as possible. And so they're just going to be static. They're going to sit there in that location as far away as possible. That means as far away as possible, that would be on the surface of this metal. That's where all those charges are going to accumulate. And so then we'd have an electric field kind of like we see here. So notice how there's these electric field lines that are going outward everywhere. Notice there's no electric field lines inside the metal. Okay, that's because there's no free charges. I want you to think about what would happen for a second. This was kind of a tough question, so you really need to be thinking here. If there was an electric field line inside the metal, what would that do to any charges that were inside the metal? How would they move compared to that field line? Or would they move? Nobody's typing. I've stumped you. Okay, so they'd either move along it. So let's say that the positive charge, they move along it, or they'd move against it if it's a negative charge. Good. But I want you to tell me something about how they would move. You know, think back to kinematics. I mean, how would they move? Describe their motion to me if you could actually see it. Yes, they'd be accelerating, right? If there is a field line, that's telling you that there must be a force. And if there's a force on a charge that's here in the middle, then that charge would start to accelerate. Okay? That acceleration, that would be a current. Those charges moving, they're moving and they're accelerating, and there would be some current there. In these cases, this is static charges. They're not moving. They quickly get in equilibrium. There's no motion. So there can't be an electric field inside the metal. Okay, so I want you to think about that. There can't be one because that would cause an acceleration of the charges inside. And there's lots and lots of charges in there. Now, they might be a net charge of 0 because there's a plus and a negative, but there's still charges in there. Okay, moving along. The first thing I need to do is I need to draw a Gaussian pillbox that kind of mirrors the surface here. And keep in mind, this encloses the volume. So I have this rectangular prism here. So it's not just a square or a rectangle. That's actually a prism. Okay, so for this one, I can also do the E.dA for this. And when I do that, I would have the E field is pointing out along the A vector. And so that's constant if I make my pillbox fairly small. And notice there's not, unlike the last one, we had an EA on the other side as well. But here we only have one EA. Then I would have the charge enclosed would be equal over epsilon naught would be equal to the EA. For this, you'd probably have some sigma, some charge per unit area. So similar to the last one. The areas will cancel out when I set these equal. And so I have sigma over epsilon naught. It's very similar to the last one, except the last one had 2 times sigma over epsilon naught. That's because we have an E field going out both sides of the pillbox. Here, because it's a metal, we're only going to have E field in one direction because we can't have an E field inside the metal. It would cause the charge to accelerate. Okay, so we have a thin, we're going to go a little bit harder now. Okay, we have a thin spherical shell of radius R naught. It possesses a total net charge Q, big Q. So that's this one right here. So you see all the positive charges on the outside of it there. And notice its radius is R naught. Determine the electric field at points A outside the shell, so that's out here, and B inside the shell, so that's in here. And what if the conductor were a solid sphere? So like a solid conductor. So this right here is just a shell, but we're going to think about a solid sphere as well. Okay, so part A, we're going to try to figure out what the electric field is outside this shell. Well, the first thing I have to do is draw a Gaussian pillbox that mirrors the charge distribution. So here we have a sphere, so I'm going to have to draw a sphere. I know, be very careful, this pillbox looks like it's a circle, but all of these are three-dimensional, so that's really a cross-section of the Gaussian pillbox. So in this case, oh, I jumped right to the answer. No, that's so annoying. Okay, so in this case, boy, I don't know how to do this. I think I'm going to have to jump out for a second. I don't like this. Boy, I wish I had my chalkboard here. Let's see. Hold on a second here. Yeah, that was the answer, Raj. I don't want to go right to the answer though. I want to talk about it a little bit. So I need to draw here real quickly. So give me a second. So here's my sphere, and this sphere has positive charges on it. So don't forget that from the thing that we just saw. I'm not going to draw a bunch because it'll take me too long, but I'll draw 4 here. Oh, Mike, where are you? Why aren't you right here next to me? I'll have to figure that out some other time, Mike. So I draw my Gaussian surface out here. So here's my Gaussian pillbox. I'll try that on the next one, Mike. Okay, so we know that Gauss's law says we have to do the sum of E dot dA and if I look at my Gaussian surface, there's going to be E field lines coming out of this. Well, I'm going to look maybe, let's say right here. There's your E field line coming out. E field. And there's a little surface element here, let's say like a little square or something on this Gaussian pillbox. There's also an A vector, and that A vector points in the exact same direction as the dA, I should say. Exactly in the same direction as the E field vector. So that E field is pointing everywhere outward. So somebody type in there, tell me something about the E field. Is it changing or is it constant through the Gaussian pillbox? It's constant. Nice. So the only thing that's changing is the area, and I have to sum up all those little tiny areas. Okay, so what is the area of my pillbox here? I don't know if you guys can say it or type it. Yeah, what is the area? Four pi, close. It's 4 pi r squared. There we go. Okay, so when I do this side over here, it's just simply going to be the E field times the sum of all those little tiny area elements, and that's going to be 4 pi r squared equals Q divided by epsilon naught. Okay, then now I'll go ahead and go back to the PowerPoint. All right. Okay, so then I get Q equals 4 pi epsilon naught over r squared. Okay. Any questions then how that answer came about? What do you notice about that that equation and what the E field is for a point charge? They're both inverse square. In fact, it's the exact same equation because 1 over 4 pi epsilon naught is K. Remember? We found that out yesterday. I had you guys do that on your calculator. So it's actually the same. Okay. Okay, now we're going to do part B, inside the shell. And so I'm going to go back to this. Okay, so now I'm going to do inside the shell. Let me do some erasing here to get rid of some stuff. Have a question here, and A vector is always, yes, Michael, I didn't see a whole question. You asked, is the A vector always perpendicular? Yes, it's always perpendicular to the surface, and it's always pointing outward. It's always pointing outward. And so it happened to be in the same direction as the, yep. Okay, so now I'm going to draw another Gaussian pillbox. This one, keep in mind that this was a shell of charge, okay? And all that charge is on the outside here, okay? So I'm going to be doing the exact same thing. Doing the exact same thing here. Gauss's law. Gauss's law says that the flux, that's this side over here, the electric flux, has two ways of calculating it. So I can sum up the E dot dA, that's the electric flux, that's that phi E. So the electric flux, that's a sum. It's also equal to Q enclosed over epsilon naught. So there's two ways you guys can find electric flux. Okay, so when I do this, again, I would be doing the exact same thing. Think about the E field here, okay? But how much charge is enclosed inside my Gaussian pillbox? How much charge is enclosed? Nada. That's right. None. None whatsoever. And so what will the E field be inside of this charge distribution? 0. That's it. The E field is 0. That's because there's no charge enclosed. Now, I'm not saying that there's not an E field perhaps over on this side here because it's closer maybe. You know, that might be. But that E field will also be canceled out by all of these. So the net E field inside is 0. Does that make sense? I'm not saying there isn't an E field vector, but then there would be another E field vector and another one, and they all cancel out and give you a net E field of 0. Yes, exactly. That is how a Faraday cage works. If you're interested, there's some videos. I think I have one somewhere. You can look at resources or something. But you can also go to, well, I don't know if you guys get to YouTube or not, but I might show some in class. I have a Faraday cage actually to do a demonstration, but it's not as cool as the ones that you can find online where you can actually put whole people inside of. They're pretty awesome. So, any other questions with this problem? Okay, so now I think, let's see, the next part we're going to be looking at if it was a solid. Okay, so I need to do some more erasing. Okay, what if this was a solid hunk of metal? You know, again, a hunk of metal, spherical, I should say. Spherical hunk of metal, and it had a charge on it. Yes, right, Raj. All the charge would be on the outside, right? Even if it was a solid hunk of metal, all the charge would be on the outside. So we have a positive charge out here, positive charge out here, positive charge out here. Okay, because those charges want to get as far away from one another as possible. Okay. Okay, first thing I want to do is I want to go ahead and do a Gaussian surface on the inside this time. I'm going to start here. Okay, so for this one then, how much charge is enclosed for this? How much charge is enclosed in my Gaussian pillbox? How much net charge? Maybe I should do it that way. How much net charge is enclosed? Nada. That's right. 0 again, right? So therefore, the E field inside of a solid hunk of metal is 0. Okay, and again, that's why a lot of times Mike was talking about a Faraday cage. A lot of times when you have very sensitive electronics that you don't want to be affected by electric fields, a lot of times they'll put it in a case that's metal. That way any external electric fields will not affect it. That's also why they say during an electrical storm that you're generally safe inside of your car. Now keep in mind, if you touch any metal, then you're also going to be part of that external surface. So I don't know an electrical storm I would want to be in a car because it's going to be kind of hard to make sure you're not touching metal. But in theory, you should be safe. Okay, so now let's go ahead and draw another Gaussian pillbox, but this time on the outside. Okay, for this one, whoops, wrong thing. Okay, so again, I'm going to have an E field coming through here, and I'm going to have a certain amount of area. And can you see again that E field is pointing in the exact same direction as my A vector? And that E field is constant everywhere through my Gaussian surface. So it's going to be E times the area of my Gaussian pillbox, which is 4 pi r squared. And that's going to be equal to the charge enclosed again, Q, over epsilon naught. Oops. Dyslexia came in. Sorry about that. Okay. Any questions about that? What was? Sorry, Raj. It's a grandmother clock we have. Okay, I'm going to go back to the PowerPoint. Okay. Oops. Not. So it's the same whether you have a shell of conductor or if you have a solid conductor. It's going to be the same no matter what. Okay, I got about 10 more minutes. Now we're going to start looking at insulators. And we've already looked at insulators. They can get a charge. For instance, those hard ebonite rods that we had, and you guys rubbed them and you got a charge on it. Remember that? So it's possible to put a charge on a non-conductor, so an insulator. But tell me something about those charges. Can they move freely? No, it can't move freely. Okay, so in this example, we have an electric charge Q, and it's distributed, it's static. It can be distributed uniformly throughout this non-conducting sphere of radius R naught. Determine the electric field A outside the sphere and B inside the sphere. I can't remember if I can just go right to the answers. I hope not. Oh, dang it. All right. So I'm going to have to go back to the Twiddless site. I'm going to have to invest some time, like Mike said, later on and figure out how to...
It's just the controls in the lower left corner. When you're
All right. I'll give it a try. All right. In the lower left hand... See, I don't see anything. What are you talking about?
Look, it's like grayed out in the lower left corner. You see 2 arrows in the lower left?
Oh, yeah. Okay. Thank you. Okay, perfect. Maybe.
Just hit backspace to
Gotcha.
To go back a slide.
Thank you. Okay, so we're going to be figuring out the E field outside here. Okay, so again, I have kind of an area here, and I'm going to have an E field through it. So here's this E field. Oh, that is much quicker. Thank you very much, Mike. And I'm going to have an A vector that's pointing in the same direction. So my A vector is that way as well. And so when I do Gauss's law, oh, I like this so much better. E times dA equals Q enclosed over epsilon naught. Can you see that E vector is going to be constant everywhere? Again, I'm hoping you guys see that. Yes? Yeah, okay. And so therefore, the only thing I have to worry about is figuring out the sum of all those A vectors. Well, that's just going to be the same thing as I've been getting, right? It's going to be E times the area. In the case here, the area is, again, 4 pi r squared, because this is a sphere. 4 pi r squared equals Q enclosed over epsilon naught. And so then I can solve this, and I get E is equal to Q over 4 pi epsilon naught over 1 over r squared. I'm putting that out there separately. Don't have to. I'm doing that so you can see that in fact, it is an inverse square relationship. Okay. And that's what I have for an answer there. Okay, now the next part of this is a little bit tougher. So I go back like this and go forward. We'll erase everything. No, it doesn't erase it, darn it. Okay. Mike, do you have any idea how I can erase things? How do I erase them?
It's probably on the menu. Hit the pen menu and see what it says.
Ah, thank you.
There's probably an erase all button somewhere.
Oh, is there?
Erase all link on slide.
Oh, perfect. Thank you. Got it. Thanks. Thanks for schooling me. You guys are awesome. Okay. So now I have to do the inside part. This is where it's going to get a little bit tougher, because can you see that when I start drawing a Gaussian surface in here, again, this is a three-dimensional surface, that not all the charge is enclosed? Can you guys see that? Type something. In other words, can you see that there is some charge out here, which is outside this Gaussian pillbox? Yeah, okay. That's the problem. So, truthfully, insulators are going to be a little bit more of a problem. They're going to be a little harder. So I have Gauss's law again. So that's where I'm going to start off with. And on this side, again, I'm going to have a certain amount of area here. So here's my area vector. I'm going to have a E field vector. Those are always going to be pointing outward because I have this net charge enclosed. So that's no different. So the left-hand side that shows the little calculus symbol, the truth is that's going to be the easier side. That's going to be the easy one. So again, it's just going to be E times 4 pi r squared. That's no different. Okay. Okay, where it gets a little bit tougher is over on this side, the Q enclosed. Okay. Ideas, because I don't want to just tell you. I want some ideas. How will I figure out the charge enclosed? The total amount of charge is Q. Has something to do with volume of the sphere, that's right. But how? Because that's right, there you go. It's a fraction. It's a certain fraction. So, for instance, let's say that the amount of volume I have enclosed in my Gaussian pillbox, let's say it's 3/4 of the whole. Can you see that the amount of charge that it would have inside of it, since it's uniformly distributed, would be 3/4 of the Q? Or let's say it was 2/3 of the volume, then it would be 2/3 of Q. So it's really going to be a ratio of the volumes. So I'm going to go ahead and put Q here over epsilon naught, but I have to do a ratio of the volumes. Well, ratio of the volumes is going to be the ratio of my Gaussian pillbox to the volume of my whole thing. Well, the whole thing is actually, you guys tell me, how do you find the volume of a sphere? How do you find the volume? 4/3 pi r cubed. That's right. Nice. So you guys are going to know those formulas by heart pretty soon if you don't know them yet. You got to get those memorized. So the volume of the sphere is 4/3 pi r cubed. And I'm going to use r naught because that's the radius of the entire thing. R naught cubed. The pillbox is going to be very similar. It's going to be 4/3 pi, but it's not going to be r naught cubed. It's going to be, the radius to this is just going to be r. That radius is r. The same radius as I have over here from my Gaussian pillbox. So this is going to be r cubed. Of course, the 4/3 cancel. The pi's cancel. And there's a r squared on this side. That r squared is going to cancel the r cubed up here and just leave me r. And so now I have e times, that's not subtract, times 4 pi equals q times, actually I'm not going to do that, over, let's see, epsilon naught r naught cubed times r. And of course I can move the 4 pi over here. The reason I separated the r out is because I want you to look at this q over epsilon naught r naught cubed. Can you see that all this is a constant? And we're almost done here. You see all this is a constant here? So what I get is the E field anywhere inside is going to be equal to Q over 4 pi epsilon naught r naught cubed, that's a constant, times r. If I were going to plot this, E versus R, what kind of relationship would Mike's anticipating my question? That's right, it's linear. It's linear. Remember back when we compared the fields and I said, let's say you were inside the Earth and the Earth was a solid sphere and you wanted to plot the gravitational field anywhere inside. And remember how I kind of fudged things and we said at the very center it was 0 and at the outside it was 10 newtons per kilogram. And I said, okay, let's connect those, and so it's linear. I know you guys were probably thinking, yeah, I don't think I like that. Here I've just proved it to you. It's linear. Okay? So any questions? Okay, now I think there is some more to this PowerPoint, but I think we're pretty close. Where are we at here? Let's see. Discard, whatever. Let's see where we at. Oh, actually, you know what? Let's do, I think we can actually do another slide. Actually, we kind of talked about some of these slides. So let's go to this side here. So anyway, here, notice R is greater than R naught. So we're talking about out here. What kind of relationship is this? What kind of relationship is that? Inverse square. I'm going to give you guys like another 30 seconds or so because I'm almost to my time limit. Nice, inverse square. So it's very similar. In fact, it's the same equation you get for a point charge. Okay. So now we're going to go ahead and go on to the next one. This is when it's inside. The Gaussian pillbox is inside of this insulator, and that's a direct relationship. Ooh. Somebody said inverse. Oh, somebody's saying direct. Somebody's saying linear. Which is it? Oops, what did Mark do? I hit it and forgot the last question. Okay, all right. So which one is it? Is it direct or linear? Michael's saying there's no intercept. That's right. So it's direct. That's right. So linear, I mean, it is linear, but you can go more than that. You can say it's direct. This is a direct relationship. Yeah. Okay, and I think I had one more slide. Let's see. What is this one? Determine electric field A outside. Didn't we already do this? Electric charge Q is distributed uniformly throughout a non-conducting sphere radius are not. Determine electric field A outside the sphere. Did that. And B inside the sphere. I'm not sure what you mean by that, Raj. I think, here I just wanted to show you what the graph would look like so you could sketch it. I think that's what this slide is. So if we wanted to do all of, graph this whole thing, this is what the graph would look like. We'd have the E field 0 at the very center of the sphere. It linearly increases to a point, and then it falls in inverse square relationship outside the sphere. Any questions? Okay, that's the end of the PowerPoint. So we're not going to do any more. I appreciate your attendance, and I hope that kind of clears things up and lets you see that this isn't going to be so bad. This Gauss's law stuff is going to be pretty easy. Any questions?
Could you go back to the slide with the cylinder for just a minute, the infinite wire?
Oh, yeah.
I just didn't finish writing that down.
Sure.
Thanks.
Yep. Is that good enough?
Yeah, just a second.
Okay. Raj has a question. If you were, I didn't see that question, Raj. Let's see here. Raj, if you were to times the E to the charges, isn't that the fourth? I'm not sure I understand.
That's good, thanks.
Okay. Raj, I'm not sure I understand your question. If you take a charge, maybe this is your question, Raj. You're wanting to know how. Right, exactly. Raj, the force is equal to the charge times the electric field. So if I were to take a point charge outside of this wire, let's say I bring a point charge right up here somewhere, and let's say it was a positive charge. If I take it right to the Gaussian surface, right at this point, and I want to know what the force is, you're absolutely right. I could do Gauss's law to figure out what the E field is right there at the Gaussian surface. And then I could multiply it by the charge, and that would give me the force on that charge. So yeah, you're absolutely right, Raj. You can use F equals QE to figure out the force on a charge. And then of course, by Newton's third law, there would be a force on the wire too, right? In the opposite direction. Does that answer your question, Raj? Okay, well, I think I've taken enough of your time, so second-year students, you can go ahead and leave if you don't have any more questions. Okay, see you. Thanks for coming.
Do we have to finish anything for tomorrow then?
You know what? Why don't you try to do the lab response, but we're still going to whiteboard it in class.